Since modeling any kind of volatility is mathematically difficult, we often use Model 3. This model assumes that volatility starts at a specific level and then fades away over time. In this setup, sigma is your starting volatility. The term e to the power of negative alpha times t acts as a decay factor. This ensures that as time moves forward, the volatility gets smaller and smaller, eventually approaching zero. Let's walk through a quick calculation to see this in action. Imagine a current interest rate of 4.50% with a drift of 0.40% per year. If our starting volatility is 2.20% and we have a decay rate of 0.60%, how does the rate change over 3 months? First, we calculate the drift, which is 0.10%. Next, we calculate the decayed volatility, which drops to 1.89% after 3 months. We multiply that by a random shock of 0.20 to get 0.378%. Adding the drift and the shock together gives us a total change of 0.478%, resulting in a new expected rate of 4.978%. Why do we go through all this math? These models are the gold standard for pricing complex derivatives like interest rate caps and floors. Because we can manually adjust the volatility for different time periods, we can make the model perfectly match the current market prices we see on our screens. Furthermore, under specific settings, this model can behave exactly like the famous Vasicek model, giving us the same terminal distribution of rates, but with added flexibility for short-term pricing. However, these models aren't without their critics. The biggest complaint is that they require us to forecast market volatility very far into the future, something that is notoriously difficult to do accurately. Because of this, many risk managers still prefer mean reversion models for long-term hedging. Those models assume rates will eventually return to a stable average, whereas our time-dependent models focus more on interpolating between today's observed market prices.